We are jumping right into a brand new deep dive today.
Glad to be here.
Yeah, and we are taking you on a microscopic journey into the hidden, completely invisible world of atomic structure.
It is a totally different universe down there.
It really is. Specifically, we are exploring a fascinating stack of visual guides detailing the inner lives of electrons and the reality of electron clouds.
Which is so relevant because if you are listening to this right now, you are interacting with technology that relies entirely on these exact principles.
Exactly, every single piece of tech. And what's compelling about the material we are analyzing today is that it doesn't just hand us a wall of dense, impenetrable text.
No, thankfully.
Right. Instead, we have this incredible series of conceptual models, really vivid diagrams, and real-world visual experiments that really attempt to make these invisible forces tangible.
Tangible and understandable.
Right. Okay. Let's unpack this because we are looking at the very building blocks of the universe, and we're trying to conceptualize how a modern power grid actually works at the quantum level.
It's a foundational topic, and I'm really glad we are tackling it for you today.
Me too.
Because understanding these subatomic components is far more than an exercise in abstract science. It is the absolute basis of how our modern electrified world functions.
Yeah, without it, we have nothing.
Right, without the mechanics we are about to explore, there are no smartphones, no electric vehicles, no server farms. Everything that hums, lights up, or computes does so because of the rules governing these microscopic particles.
It's all connected.
It is. By deconstructing the conceptual models we have in front of us today, you are essentially looking at the blueprint for the entire modern age.
That is a wild way to think about it. So let's start by looking at how the materials guide us from a very classic, almost comfortable understanding of the atom to something much more complex.
The transition is really stark in these guides.
Yeah, the initial diagrams present that familiar retro image of an atom. We see the central cluster, the nucleus.
Right, made up of bright red protons and blue neutrons.
Exactly. And surrounding that core, we have these neat concentric circular tracks. They look like perfectly drawn rings. And riding on those tracks are little green electrons.
It's a very iconic image.
It looks exactly like a tiny, highly organized solar system. The protons and neutrons are the sun in the middle, and the electrons are planets quietly orbiting on their predictable, fixed paths.
It's an incredibly orderly, deterministic way to look at the universe.
It really is. It feels safe.
Which is exactly why that specific model has been used to teach the concept for decades. It gives the human brain a clean, mechanical system to grasp.
But
What's fascinating here is that orderly little solar system model isn't the reality of what is happening down at the atomic level.
not at all.
No, and the visual guides we are analyzing do a brilliant job of correcting this oversimplification. If we follow the progression of the conceptual models, there is a deliberate, striking transition.
You can literally see it change on the page.
Exactly. Those neat, sharp circular tracks begin to blur. They start developing this hazy halo around them.
It gets really fuzzy.
And then the rings disappear completely. Instead of fixed paths, the entire area surrounding the nucleus turns into a scattered gradient texture.
It looks like a thick fog.
Right. And one of the specific diagrams featuring this textured, static-filled field is explicitly labeled electron cloud.
The shift from the sharp lines charting the course of the green electrons to this hazy gradient cloud is honestly kind of jarring. The solid little dots are just gone.
Replaced by this aura.
Yeah, it's almost like the atom has lost its solid edges entirely. But why make this conceptual shift? I mean, if the planetary model works so well for basic understanding, what is the scientific necessity of pushing us into this foggy, blurry cloud territory?
It's a necessary shift because it represents a massive leap in our understanding of physics. The cloud model is showing us that electrons don't actually move in perfect, predictable rings like train cars on a circular track.
They aren't just doing laps.
No, they aren't. You cannot point to a single fixed location and say, the electron is exactly here right now, and it will be over there in 1 microsecond.
Because it's too fast?
Well, not just fast. They actually exist in these blurry zones of probability. The cloud represents where an electron might be.
Might be.
Yes. In the areas where the gradient is darkest and thickest, which is usually closer to the nucleus, the probability of finding an electron is much higher.
Right.
As the gradient fades out toward the edges, that probability drops. It's a messy, chaotic, and totally dynamic reality.
So they're just buzzing around.
The electrons are swarming in a three-dimensional space, popping in and out of predictable existence based on energy levels. Visualizing it as a cloud of probability density is much closer to the truth of quantum mechanics than visualizing it as a planetary orbit.
So we basically have to completely discard the idea of the electron as a tiny green marble rolling along a track. We have to think of it as a vibration or a smear of potential energy surrounding the nucleus.
That reframes how you look at physical matter entirely.
It really does. Every solid object around you is just a vast collection of these vibrating, fuzzy probability clouds holding together.
It's mind-bending when you really sit with it.
But our source material doesn't stop at just observing the atom in its natural resting state. It introduces action.
It introduces manipulation.
Yes.
Mhm.
And here's where it gets really interesting, because the next set of diagrams introduces a classic macroscopic tool.
The U-shaped horseshoe magnet.
Exactly. We see this classic red and blue magnet labeled NNS moving in very close to our atom. It's literally bridging the gap between objects we could hold in our hands and these microscopic probability clouds.
That transition is crucial. We move from theoretical atomic structure to practical applied physics.
Right.
The horseshoe magnet is a universally understood symbol for magnetic force, and the guide uses it to demonstrate how outside energy fields interact with the atomic structure. We are looking at the very mechanism of manipulation.
And the visualization of that manipulation is quite aggressive. The model shows distinct, wavy red lines, representing the invisible magnetic force field reaching out from the poles of the magnet and penetrating the space of the atom.
It looks like energy waves striking the outer edges of the electron cloud.
Yeah, and as those force lines hit, the visual shows one of the electrons being pulled completely out of the atomic structure,
Just rip.
ranged away from the nucleus, floating out into the empty space. And the guide explicitly labels this runaway particle free electron.
Right.
But if the electron is just existing in a blurry cloud of probability, how does the magnetic field actually lock onto it and rip it away?
That's the core of the interaction. The magnetic force isn't grabbing a physical marble, it's interacting with the electromagnetic charge of the electron itself.
Okay.
The wavy lines represent a transfer of energy. You see, the nucleus of the atom has a positive charge, which is constantly pulling on the negatively charged electrons, keeping them trapped in that probability cloud.
Like a gravitational pull, almost.
Similar concept, yeah.
Yeah.
But when you introduce a strong external magnetic field, you are introducing a competing force. The magnetic field imparts energy into the system, and if that energy is strong enough, it overpowers the attractive force of the nucleus.
It breaks the hold.
It collapses the probability of the electron staying near the core, forcing it to detach. By pulling that electron out of its cloud, we have created a free electron.
A free electron.
And this exact ability to detach an electron using a magnetic field is the critical first step in generating power. Every generator and every power plant across the globe relies on manipulating magnetic fields to strip electrons away from their atoms.
So if we couldn't create that runaway particle, we would have zero electricity.
None. The modern world would go dark.
That isolated interaction, energy overcoming the nuclear binding force to strip a single particle, is the basis of our entire power grid.
It is the spark.
But obviously, a single runaway electron doesn't power a city.
No, it doesn't.
To get actual electricity, you need to corral a massive crowd of them, which is exactly where the guide takes us next. We move from the isolation of a single atom to a macro-level structure.
The copper cylinder.
Yes, a solid, copper-colored cylinder or tube. Inside this copper tube, the visualization shows it absolutely packed with these little purple circles. Each one carries a minus sign and is labeled E.
Representing a massive concentration of our newly freed electrons.
Exactly. And the crucial detail here is the overlay of black arrows pointing perfectly in the same direction, indicating that all these E particles are moving smoothly together down the tube.
What we are looking at is the visual definition of current flow.
Right.
Once you use magnetic force to strip electrons free, they need an environment that allows them to move.
A highway.
Exactly. When placed in the right kind of atomic structure, represented here by the copper tube, the energy pushes them and they begin to flow together in a coordinated stream. That organized movement of free electrons through a physical material is exactly what electrical current is.
And when a material allows electrons to flow freely and easily from atom to atom like that, we classify that material as a conductor.
Copper is one of the most efficient and widely used conductors on the planet due entirely to how its atoms are structured.
It's the ultimate current highway. All those electrons just cascading along the copper road. But the source material is quick to contrast this smoothly flowing highway with some very distinct roadblocks.
You need roadblocks to control the traffic.
Right. Right alongside our perfect copper conductor, the guide presents completely different materials. We see visual representations of everyday items. There's a black rubber tire,
A classic example.
a brightly colored plastic beach ball,
Yep.
and a cross-section of a wooden log. But hovering over these materials is a massive red X, cutting right through the directional arrows that were supposed to represent flow.
The concept of stop is absolute here.
Absolutely zero flow allowed.
The contrast is necessary to understand how we actually control power. Not all materials are created equal when it comes to their atomic structure. While the copper tube is a highway that facilitates movement, the rubber tire, the plastic, and the wood are dead ends.
The insulators.
Right, they are what we call insulators. The current flow completely stops when it encounters them.
But why use a beach ball or a car tire to explain quantum mechanics?
It's really fascinating how the guide grounds this abstract physics in such mundane, macroscopic objects.
It makes it real for the reader. And if we connect this to the bigger picture, the reason the guide uses those specific everyday items is to emphasize that the macroscopic properties of a material are entirely dictated by its microscopic atomic grip.
Atomic grip. I like that.
Why does a plastic beach ball stop current, but a copper pipe lets it flow? It all circles back to those initial images of the probability clouds.
Oh, because of how tightly the nucleus holds the electrons.
Exactly. The atoms that make up rubber, plastic, and wood are structured with incredibly stable electron configurations.
Yeah.
The nucleus of a rubber atom holds onto its orbiting electrons very tightly. Their grip is formidable.
So they won't let go.
Right. When you expose them to an electromagnetic force, those electrons don't easily break free. They stay locked securely in their probability clouds.
So the copper atoms are structurally generous.
Very generous. Their outer electrons are loosely bound, making them incredibly easy to strip away and push down the highway. Meanwhile, the atomic structures of plastic and wood are incredibly stubborn. They refuse to let their electrons go, no matter how much force you apply.
Exactly. And if you can't break an electron free from its probability cloud, you have no runaway particles. No free electrons means there is nothing to move down the line. Therefore, you have absolutely no current flow.
That stubborn atomic grip is the defining characteristic of an insulator.
Spot on.
Which brings us to a really compelling synthesis of everything we've looked at today. The final piece of our visual puzzle shifts away from these clean digital diagrams and presents a photograph of reality.
The real-world application.
Yeah, we are looking at a literal physical workbench or a green cutting mat. In the background, there's a thick, shiny spool of copper wire wrapped around a core.
Our conductor.
Right, and in the foreground, a pair of hands holds thin black and red electrical wires. The ends of these wires have small metal alligator clips, and those clips are carefully gripping the tiny metal legs of a small LED light component.
It's a highly practical, hands-on setup.
Very hands-on.
Yeah.
But looking at it now, through the lens of everything we just discussed, it's not just a workbench anymore. It's a macroscopic manipulation of quantum mechanics.
It serves as the ultimate proof of concept.
It really does.
The visual guide has walked us from the abstract theory of a solitary probability cloud all the way to a physical workbench where those invisible rules are actually weaponized to do work.
Weaponized is a great word for it.
Every single object on that workbench only functions because of the microscopic behaviors we just broke down.
Let's trace the path. Look at that thick spool of copper wire sitting in the background. Based on our conductor models, we know that spool isn't just inert metal. It is a massive, dormant reservoir of easily freed electrons.
Waiting to be pushed.
Because it's copper, the atoms have that loose grip, just waiting for an external force.
Right. If you were to introduce a moving magnet to that copper spool, which is the fundamental mechanism of a generator, you would agitate all those electron clouds.
You'd cause chaos in there.
You would overpower the atomic grip, rip countless free electrons away, and initiate a massive current flow.
A wave of energy.
And then look closely at the wires being held in the person's hands. They aren't just bare metal. They are coated in plastic and rubber.
Our insulators.
Yeah.
The stubborn atoms.
Precisely. The insulators act as a containment field.
They keep the traffic on the road.
Exactly. They ensure the flowing river of electrons stays strictly inside the metal wire highway and doesn't escape into the person's hands or short-circuit into the environment.
The engineering relies entirely on that contrast, using the generous copper atoms to facilitate the flow and wrapping them in the stubborn plastic atoms to control the direction.
It's all about control.
And then the journey ends at the alligator clips. They act as a physical bridge, piercing the boundary of the insulation to guide that organized flow of free electrons directly into the metal legs of the LED.
To do the actual work.
Yes. The energy that was stripped from a probability cloud by a magnetic field is finally transferred into the component to create light before the electrons continue their cycle. Everything happening on that mat is just managing the behavior of things so small we will never be able to actually see them.
It highlights the sheer scale of the engineering.
It really does.
We have harnessed the chaotic probability of the quantum realm and structured it into a reliable, predictable system that powers human civilization.
It fundamentally changes how you view the built environment around you.
Oh.
To wrap up this microscopic journey, we started by looking at the classic deterministic model of the atom, only to realize that reality is much messier.
Much more dynamic.
We entered the fuzzy, dynamic world of electron clouds, representing the probability of where an electron might exist.
We left the neat rings behind.
Then we examined the violent magnetic jailbreak, watching external energy overpower the nucleus to rip a free electron away. We saw how a coordinated crowd of those free electrons creates a current highway through conductors like copper.
While the tight atomic grip of insulators like rubber and plastic act as total roadblocks.
Exactly. And finally, we saw those principles practically applied on a real-world workbench. So what does this all mean?
It means that the next time you turn on a lamp or start your electric vehicle or plug in a server, you should visualize what is actually happening behind the wall.
The hidden dance.
Every switch you flip relies entirely on the chaotic dance of these tiny electron clouds. It relies on our ability to use forces like magnetism to rip particles free, and our understanding of exactly which materials will encourage that flow and which materials will safely block it.
It's all atomic manipulation.
Your modern life is a continuous and visible choreography of atomic manipulation. And before we conclude, I want to leave you with one final angle to ponder regarding this continuous process.
Well, let's hear it.
We spent this time analyzing the electron that gets away.
The runaway particle.
Right. We've seen how magnetic fields can pull an electron away from its home nucleus to create that vital current flow. But consider the atom that was left behind in the generator. It just lost a fundamental piece of its structure.
Yeah, I thought about that.
When you strip away that negative charge, the balance of that atom changes. So what happens to the microscopic structure and the overall stability of a physical material when countless billions of its atoms are constantly having their electrons ripped away and replaced just to keep the lights on?
That is a fascinating and heavy concept to leave us with.
Something to think about.
Definitely something to explore further on your own. Thank you so much for joining us on this deep dive into the hidden mechanics of the atomic world. Keep wondering, keep exploring, and we will catch you on the next one.